stiffness of an electrical source is typically described by its source impedance. This is the opposition to the flow of alternating current, or AC, that the source exhibits. A higher source impedance indicates a softer source, while a lower source impedance indicates a stiffer source. A low source impedance means that the source can provide a relatively high amount of current without experiencing a significant voltage drop. This type of source is often referred to as a stiff source because it can maintain a nearly constant voltage under varying load conditions. A high source impedance means that the source has a higher resistance to the flow of AC current. This type of source is often referred to as a soft source because it can experience a significant voltage drop under varying load conditions. In electrical engineering, source stiffness is also known as internal impedance, output impedance, and Thevenin equivalent impedance. The source impedance can have a significant impact on the performance of an electrical system. A low source impedance is generally desirable for applications where a constant voltage is required, such as power distribution systems. High source impedance can be beneficial in applications where voltage regulation is not critical, such as lighting circuits. Source impedance affects how a voltage source responds to changes in the load connected to it. Understanding source impedance is crucial for designing stable and efficient electrical circuits. It helps predict voltage drops, current flow, and overall system performance. Firstly, consider a power supply with a low source impedance. When a load is connected, the voltage remains relatively constant, regardless of the current drawn. This is ideal for powering sensitive electronic equipment that requires a stable voltage. Secondly, imagine a battery with a high source impedance. As the load increases, the voltage drops significantly, which can cause malfunctions or unreliable operation. This is why batteries are often not suitable for applications requiring high current and stable voltage. Thirdly, the concept of source impedance extends beyond simple voltage sources. It also applies to signal generators, amplifiers, and other electronic circuits. In each case, the source impedance determines how the circuit interacts with its load. Source impedance is a critical parameter in impedance matching, a technique used to maximize power transfer between two circuits. When the source impedance is equal to the load impedance, maximum power is delivered to the load. This is important in applications such as radio frequency or RF communication and audio amplification. Thevenin's theorem provides a method for simplifying complex circuits into a voltage source in series with a single resistor, which represents a Thevenin equivalent impedance. This allows engineers to easily analyze the behavior of the circuit under different load conditions. Similarly, Norton's theorem provides an equivalent circuit consisting of a current source in parallel with a resistor representing the Norton equivalent impedance. Both Thevenin's and Norton's theorems are valuable tools for understanding and predicting the performance of electrical circuits. Measuring source impedance can be done using various techniques. One common method involves applying a known load to the source and measuring the resulting voltage drop. By calculating the change in voltage divided by the change in current, the source impedance can be determined. Another method involves using an impedance analyzer, which directly measures the impedance of the source over a range of frequencies. This provides a more comprehensive characterization of the source impedance. Source impedance can also affect the stability of feedback amplifiers. A high source impedance can cause oscillations or instability, especially when combined with capacitive loads. Therefore, it's important to carefully consider the source impedance when designing feedback amplifiers. In power distribution systems, a low source impedance is essential for providing a stable voltage to all connected loads. This is typically achieved through the use of large transformers and conductors, which minimize the impedance of the distribution network. In audio systems, the source impedance of the amplifier should be matched to the impedance of the speakers to ensure optimal power transfer and sound quality. Mismatched impedances can result in reduced power output and distortion. When designing power supplies, it's important to consider the source impedance of the input power source. This can affect the performance of the power supply and its ability to regulate the output voltage. In high-frequency circuits, source impedance becomes even more critical due to the effects of parasitic capacitance and inductance. These parasitic elements can significantly alter the impedance characteristics of the circuit and affect its performance. Source impedance is also an important consideration in grounding systems. A low impedance ground connection is essential for preventing electrical noise and ensuring safety. In summary, source impedance is a fundamental concept in electrical engineering that affects the performance and stability of electrical circuits. Understanding source impedance is crucial for designing efficient, reliable, and safe electrical systems. By carefully considering the source impedance, engineers can optimize the performance of their circuits and ensure that they meet the required specifications. The impact of source impedance also extends to power quality. A high source impedance can exacerbate voltage sags and swells, which can damage sensitive equipment. Therefore, maintaining a low source impedance is important for ensuring power quality. In industrial applications, source impedance can affect the performance of motor drives and other power electronic equipment. A low source impedance is generally desirable for these applications to ensure stable operation and prevent voltage dips. The source impedance of renewable energy sources, such as solar panels and wind turbines, can also impact the stability of the power grid. Careful control of the source impedance is necessary to integrate these sources into the grid without causing instability. In medical devices, source impedance is an important safety consideration. A high source impedance can limit the amount of current that can flow through a patient in the event of a fault, reducing the risk of electrical shock. Source impedance is also relevant in the design of radio frequency identification or RF systems. The impedance of the reader and the tag must be matched to ensure efficient communication. In telecommunications, source impedance is important for signal integrity. Mismatched impedances can cause signal reflections and distortions, which can degrade the performance of the communication system. Source impedance also plays a role in electromagnetic compatibility, or IMC. A high source impedance can make a circuit more susceptible to electromagnetic interference, or EMI. Therefore, controlling the source impedance is important for ensuring that the circuit meets EMC requirements. The effects of temperature on source impedance should also be considered in some applications. The impedance of some components can change significantly with temperature, which can affect the overall source impedance of the circuit. In aerospace applications, source impedance is a critical consideration due to the stringent reliability requirements. Careful control of the source impedance is necessary to ensure that the system operates reliably under extreme conditions. The concept of source impedance can be applied to various types of electrical sources, including AC power sources, DC power sources, and signal generators. Each type of source has its own unique impedance characteristics. When choosing a power supply for a particular application, it's important to consider its source impedance. A power supply with a low source impedance is generally preferred for applications requiring stable voltage and high current. The source impedance of a power supply can be affected by various factors, including the design of the power supply, the components used, and the operating conditions. In some cases, it may be necessary to add external components to reduce the source impedance of a power supply. Source impedance is also an important consideration in the design of filters. The impedance of the source and the load must be considered when designing a filter to ensure that it performs as expected. When connecting multiple devices to a single power source, it's important to consider the source impedance of the power source and the input impedance of the devices. Mismatched impedances can cause problems such as voltage drops and signal reflections. Source impedance can also affect the transient response of a circuit. A high source impedance can slow down the transient response, while a low source impedance can improve it. In some applications, it may be necessary to use a buffer amplifier to isolate the source from the load and reduce the effects of source impedance. Source impedance is a complex topic that requires a thorough understanding of electrical circuit theory. However, by understanding the basic principles of source impedance, engineers can design better electrical systems. The concept of damping factor is closely related to source impedance. A higher damping factor indicates a lower source impedance in a more stable system. In control systems, source impedance can affect the performance of the controller. A poorly designed controller can actually increase the source impedance, leading to instability. The source impedance of a measurement instrument can affect the accuracy of the measurement. Therefore, it's important to choose a measurement instrument with a low source impedance. In some cases, it may be necessary to use a voltage follower to isolate the source from the measurement instrument and reduce the effects of source impedance. The source impedance of a communication channel can affect the signal-to-noise ratio, or SNR. A mismatched impedance can cause signal reflections, which can reduce the SNR. Source impedance is also relevant in the design of impedance transformers. An impedance transformer is a circuit that is used to match the impedance of the source to the impedance of the load. The source impedance of a transmission line is called the characteristic impedance. The characteristic impedance of a transmission line is determined by the physical properties of the line, such as its inductance and capacitance per unit length. Source impedance is a parameter to consider when analyzing a system. A low source impedance typically indicates a stiffer source. A stiff source has a high ability to maintain its output voltage, regardless of the current that is required by the electrical load. There are three factors that can be adjusted to affect the source impedance. Firstly, the wire gauge to lower resistance. Secondly, increase capacitance to assist with changes in current demands. And thirdly, by stiffening the voltage regulator. The voltage regulator in a power supply strives to maintain a constant voltage at its output, despite changes in input voltage or load current. The effectiveness of the voltage regulator in achieving this goal is directly related to the source impedance. A voltage regulator with a lower source impedance can more effectively compensate for changes in load current and maintain a stable output voltage. Some voltage regulators incorporate feedback mechanisms to adjust their output voltage based on the load current. These feedback mechanisms can help to reduce the source impedance and improve the voltage regulation performance. Voltage regulators are crucial in many electronic devices and circuits to ensure stable and reliable operation. They are used in a wide range of applications, from simple power supplies to complex electronic systems. The choice of voltage regulator depends on the specific requirements of their application, such as the input voltage range, the output voltage, the load current, and the desired level of voltage regulation.